On October 4, 2025, a photograph from Mars changed everything. The Perseverance rover captured something in the Martian sky, an elongated glowing object, 4 times longer than its width, causing an internet frenzy. For several hours, 2 camps formed. On one side, Aviv Loeb from Harvard explained it as a common optical illusion created by overlapping images. On the other side, Dr. Horace Drew, a scientist from Caltech in Cambridge, claimed that the mathematical calculations do not add up. If there is a green nickel lump around this object, then the center should be green, but it is white. And here is where it gets interesting. NASA fell silent. Then the European Space Agency went quiet, and later China, which always publishes Martian images for propaganda. Even the United Arab Emirates, 4 competing space agencies vying on the world stage, all refusing to reveal what their Martian orbiter saw during the closest approach in history. Is this coincidence? NASA suspended its work on October 1st, exactly 48 hours before the flights. Convenient. And now, as the comet Tri-I Atlas approaches the Sun, reaching perihelion on October 29th, we face 2 possibilities. Either this is the most unusual comet ever discovered, ejecting industrial-grade nickel alloys and contradicting all known natural explanations, or something much stranger is happening over Mars. In this video, we will analyze the evidence that both sides do not want you to see: photographs, silence, anomalies, and why October 29th could become the day everything changes. If you are as intrigued by this as I am, like and subscribe to stay updated. Comment where you are listening from, what time it is for you, and which explanation seems more convincing: a camera artifact or something entirely different. And if you want to help our community grow, share this on social media. Thank you for your support. Chapter 1. The photographs that changed everything. Let's start from the beginning, or at least from what feels like the beginning for most of us. October 4th, 2025. A date that will either enter history as a turning point in human understanding or become another example of our fanciful speculations. The verdict has not yet been delivered, and it is this uncertainty that makes the situation so thrilling. The Perseverance robot, located in the Jezero crater on Mars, was aimed at an unusual task. For several days, engineers on Earth prepared for this moment. The third confirmed interstellar object, designated Tri-I Atlas, was approaching Mars at a distance of 38 million kilometers, practically a handshake in cosmic terms. This was humanity's best chance to get a good look at something that came from beyond our solar system, from the infinite darkness between the stars, where we had never sent a probe, never captured an image, and never truly understood what might be there. The rover's right navigation camera, or NavCam, began its operation. These are not bright color cameras that allow us to enjoy stunning panoramas of the Martian surface. NavCam is more utilitarian. Its task is to help the rover navigate, avoiding obstacles and planning a route through the rusty terrain. It takes black and white photographs with an angular resolution of 0.33 millimeters per pixel. These technical specifications mean little until you understand what they represent at a distance of 38 million kilometers, about 12,500 kilometers per pixel. Think about this for a moment. Each pixel of the image represents an area larger than the diameter of the Earth. You won't see fine details, can't count the windows on the spacecraft, or read the serial numbers. However, you will be able to discern the overall shape of something, especially if you combine several images to reduce noise and enhance the signal. And that is exactly what happened. The Perseverance team, or perhaps more accurately, astrophotography enthusiasts, began to combine frames from NavCam, not 2 or 3 images, but hundreds taken over about 10 minutes of Martian time. The process of layering frames is widely used in astrophotography. When trying to capture something faint, you can take multiple exposures. Random noise is averaged out, but real signals are combined. This is how astronomy enthusiasts capture nebulae with home telescopes. Our professionals isolate the faintest galaxies at the edge of the observable universe. When these images were combined, something emerged. Not a round dot, not a blurry smudge with a tail like the comets we have ever seen from Earth. No, what appeared was a stripe, an elongated object, 4 times longer than it was wide, glowing against the stars, and critically, it seemed white in the center, with hints of green around the edges. The image instantly spread across social networks, with streams of hundreds of comments appearing on Reddit, and astronomy enthusiasts, conspiracy theorists, professional scientists, and everyone else eager to share their opinions became active on X, formerly known as Twitter. YouTube channels rushed to analyze pixels, enhance contrast, draw conclusions, and at the center of this discussion arose a question that seemed simple but held immense significance. What are we actually looking at? The main explanation appeared quickly. Avi Loeb, a Harvard astrophysics professor and director of the Galileo project, has been tracking a triple object since its discovery in July. He has already published works claiming that the object exhibits unusual, anomalous properties that do not quite fit the profile of a typical comet. But when the image of Perseverance went viral and people began to ask whether it was a cylindrical spacecraft, Loeb turned to his blog to explain what he thought was happening. The elongation in question turned out to be an artifact, not related to alien technology, but a simple physical phenomenon and the characteristics of camera operation when objects are in motion. The three eyes of Atlas moved at a speed of about 67 kilometers per second relative to the Sun, on a retrograde orbit, in the opposite direction to Mars's movement. From Mars's perspective, this object flew across the sky at an incredible speed. In 10 minutes, he covered about 50,000 kilometers. If you combine hundreds of individual frames taken during this time, it effectively creates a time-lapse effect. The movement of the object is blurred across the final image, creating an illusion of elongation. It resembles photographing a car passing by at night with a long exposure. The car itself may be compact, but in the photograph, it appears as a light streak stretched across the frame. The headlights and taillights leave trails. One cannot conclude that the machine is ribbon-shaped just because it looks that way in the photograph. Loeb meticulously calculated all the data. The angular resolution of the navigation camera meant that each pixel covered 12,500 kilometers at the distance of the three eyes of Atlas. The stripe appeared to be about 50,000 kilometers long. Dividing this by the object's speed relative to Mars, which is about 91 kilometers per second, considering their movements, results in about 9 to 10 minutes. Each value matched the integration time needed to accumulate enough frames to elevate a faint object above the noise level. All calculations were confirmed. The explanation was elegant, simple, based on well-known principles of imaging and motion. The case is closed, right? But not for everyone. Dr. Horace Drew, who uses the alias Red Collie online, is a person hard to ignore. His resume includes work at the California Institute of Technology and a molecular biology lab in Cambridge. He published research on DNA, crop circles, and what he calls alien computer codes. For some, he is an unconventional thinker, willing to explore ideas rejected by the mainstream. For others, he has gone too far into speculation. However, his counter-argument to Loeb's explanation caught attention as it focused on something observable in the images themselves. Drew noticed that the colored versions of the layered images revealed something important. The center of the strip appeared white, while the edges had a greenish tint. He claimed that this was consistent with the observations of the three eyes of Atlas from ground telescopes, which showed a green comet rich in nickel, surrounded by a gas cloud enveloping its core. If the elongation was purely an artifact of overlaying images of a small stone sphere passing through a larger green comet, then when side-combining these frames, the central strip should predominantly appear green. In each frame, so much green from the coma accumulated that the final composed image could not maintain a bright white center. Drew suggested that the object might have an elongated white shape, similar to an egg, which is significantly larger than the green coma surrounding it. In this case, the overlay of images will maintain the white predominance in the center, as each individual frame contains more white material than green. This is a geometric argument about relationships and how colors combine when overlaying images, and it is not easy to dismiss without detailed modeling of what the extent and brightness of the coma would be at such a distance, what she would look like in black and white navcam photos that were later colorized, and what the actual size and shape of the core might be. Drew also emphasized that several orbital Mars spacecraft from different countries took photographs during flybys. Mars Reconnaissance Orbiter, Mars Express, ExoMars, Trace Gas, Orbiter, China's Tianwen-1, and the Hope probe from the United Arab Emirates all directed their instruments at Atlas during its closest approach on October 3rd. Nevertheless, by October 6th, when Drew and others published their analyses, no official processed images had been released by any space agency. Raw navcam footage from Perseverance was available to the public, as NASA automatically posted them. but high-quality images from the HIRIS camera on the Mars Reconnaissance Orbiter, which could provide a resolution of 30 kilometers per pixel from 31 Atlas, remained unpublished. Spectroscopic data that could reveal the chemical composition of the coma, colorful images from Cassis on ExoMars, infrared observations from HOPE, all remained behind closed doors. Why such silence? NASA's answer was simple. The U.S. government entered a partial shutdown on October 1st, 2 days before the launches. Thousands of NASA employees were placed on unpaid leave, websites were not updated, press releases were not prepared. The agency, by its own words, operated with a minimal number of employees focused only on critically important tasks. The processing and release of images of an interstellar comet, as scientifically interesting as it may be, apparently did not relate to critically important activities during the funding shortage. However, many considered this time suspicious. The pause began exactly 48 hours before the most anticipated astronomical event in recent years. It seemed too convenient and did not explain why ESA, the European Space Agency, which operates independently of American budget policy, also remained silent. Or why China, which usually publishes images from its Mars missions as a source of national pride and to showcase its space program capabilities, has published nothing. Or why the UAE, eager to showcase the success of their HOPE mission to Mars, the first Arab interplanetary probe, did not take the opportunity to show the world what their instruments had recorded. It was not just one organization that was hesitating. It was a silent agreement among geopolitical rivals, countries competing for prestige, funding, and influence in space exploration. This silence, more than any single photo, became the most significant part of the story. Since there were no official data, speculation filled the resulting void, and with the emergence of an object called the 3I Atlas, there was already something to talk about. Chapter 2. Two options, one truth. The debates took the form of a scientific duel, unfolding not in peer-reviewed journals with their lengthy review processes, but in real time on blogs, social media, and spontaneously organized video conferences. This is not how astronomy usually works. Observations are conducted, data is carefully analyzed, articles are written, then sent, edited, and ultimately published. This process requires time and patience. Review ensures that errors are identified, alternative explanations are considered, and conclusions are based on facts. However, with the three-eyed Atlas, such luxury was absent. It was moving. Every day it traveled millions of kilometers, approaching the Sun, preparing for perihelion on October 29th. After this, he will again deviate and begin the journey back from the solar system, accelerating as he moves away from the Sun's gravitational pull, ultimately leaving our stellar neighborhood forever. The observation window, for gathering data and understanding what he truly represented, was closing, and the debates were happening at high speed, with scientists, astronomy enthusiasts, and interested observers speaking simultaneously. The main question seemed deceptively simple. Was the elongated shape in the images a real physical characteristic of the three eyes of Atlas, or an optical illusion created during the capture and processing of the images? To understand why this is important, one must realize what each of these answers implies. If this is a camera artifact, then the three-eyed Atlas is likely a relatively compact object, possibly a few kilometers in diameter, surrounded by a sparse coma of gas and dust. It is unusual, certainly, considering its interstellar origin and chemical composition, but ultimately, it is a comet. Strange chemistry, yes, unusual trajectory, of course, but still, this is a natural object formed in another star system billions of years ago, ejected due to gravitational interactions and now randomly passing through our solar system. If this is not an artifact, and the object indeed has an elongated structure, then the conversation changes radically. Natural objects in space tend to take on certain shapes. Small bodies usually have irregular shapes like asteroids, as their gravity is insufficient to become spherical. These bodies become spherical or flattened spheres if they rotate quickly. An extension in a 4-to-1 ratio for natural objects is rare, not impossible, but requires specific formation scenarios or structural compositions capable of supporting such shapes against gravitational collapse or tidal forces. The elongated structure immediately evokes associations with Oumuamua, the first confirmed interstellar object discovered in 2017. Oumuamua also had an elongated shape, its size estimated at about 10-to-1, based on how its brightness changed while rotating in space. This elongation sparked endless debates. Some argued that it was a cigar-shaped asteroid. Others suggested it could be a flat disk, visible from the edge like a pancake, while Avi Loeb proposed the controversial idea that it might be a solar sail, a thin, artificial structure designed to move under the influence of light. The elongation of Oumuamua, combined with its non-gravitational acceleration upon leaving the solar system, an acceleration that could not be fully explained by evaporation like that of a typical comet, made it anomalous. The scientific community mainly leaned towards exotic yet natural explanations, the evaporation of invisible hydrogen or the sublimation of solid nitrogen ice in an unusual manner. But the discussion remained unresolved, and Loeb continued to insist that artificial origin should not be dismissed without evidence. Now before us was the three-eyed atlas, which potentially displayed elongation again. If this is true, it will become the second elongated interstellar object out of only 3 ever discovered. This is already a pattern. 2 out of 3 is 67%. If elongated forms are rare among natural objects but common among interstellar visitors, the question arises: why? What makes interstellar objects special? Do we see the effect of selection when only certain forms survive being ejected from their home systems and during their journey through interstellar space? Or are we witnessing something entirely different? The mathematical arguments became increasingly complex. Several astrophysicists, not directly involved in the debates between Loba and Drew, began conducting their own simulations. If you model the three-eyed atlas as a point source, effectively considering it as a star, and then track how this point moves across the Martian sky for 10 minutes, you can create synthetic images. Blurring each position considering the navigation camera's resolution and their overlay is what needs to be done. These simulations mainly supported the explanation of the artifact. A moving point source, when tracked and overlaid, forms an elongated line. The length of this line corresponds to the distance traveled during the exposure time. This is basic kinematics plus image processing. However, assumptions were made in the simulations. It was assumed that the three-eyed atlas is a point object, with its brightness concentrated in a small core. What if the coma was extensive? What if it already reached tens or hundreds of kilometers in diameter? Then each frame captures not a point, but a blurred disk. The layering of blurred disks over time produces a different result than layering points. The line becomes blurred, less distinct. The distribution of brightness changes. And here, it becomes interesting. The images showed relatively clear boundaries on the elongated object. Not perfectly clear, but sharper than one might expect from the image of a large blurred comet moving across the frame. This sharpness suggested that the coma could be smaller than expected. The core, brighter relative to the coma, or the structure was indeed elongated. Then the color analysis began. This moment of the white center and green edges was hard to ignore. Other astronomy enthusiasts began to extract their ground observations from early September when the three-eyed atlas was photographed during a total lunar eclipse. These images, taken with tracking telescopes that compensate for the object's movement, showed a three-eyed atlas with what seemed to be an elongated white core in a green halo. An astrophotographer, Gerald Raymond, who had photographed comets for decades, noted that the structure appeared atypical. Most comets display a bright nucleus with a gradually fading coma, more round or slightly elongated towards the sun due to radiation pressure, pushing dust away. The three-eyed atlas looked different in its images. The white area appeared elongated even with proper tracking, while the green coma seemed to form a separate layer around it, rather than a uniform glow. If taken seriously, these terrestrial observations indicated that the elongated white appearance was not merely an imaging artifact. It was already visible from Earth, though difficult to discern due to significant distance and atmospheric distortion. Professional astronomers began to speak cautiously. Some noted that determining the true shape of a comet from Earth, or even from Mars's orbit, is challenging. You do not see the solid core directly, but observe sunlight scattered by dust and gases around the core. The distribution of this dust and gas depends on how the core emits gases, which is influenced by its rotation, surface composition, angle of sunlight, and a dozen other factors. A spherical core with uneven gas emissions from active regions can create asymmetrical comas that appear elongated. But others noticed that the three-eyed atlas had already shown its unusualness in many aspects beyond just the debates about form, and it is here that the conversation begins to expand beyond the two options related to photography. The chemical composition continued to surface in discussions. Space observations with the James Webb Telescope in early August revealed something unexpected. Most comets are rich in water ice. As they approach the sun, the water sublimates from the surface, creating characteristic tails. But the three-eyed Atlas was different. The Webb spectrograph showed that the coma was dominated by carbon dioxide rather than water. 87% carbon dioxide by mass, 9% carbon monoxide, and only about 4% water. This ratio, 8 to 1 of carbon dioxide to water, was extreme. Comets in the solar system usually show the opposite ratio, significantly more water than carbon dioxide. Some comets from the distant corners of the solar system, located in the cloud of water, show increased carbon dioxide content, but nothing like that. The only other interstellar comet, the two-eyed Borisov, exhibited water-dominant chemistry similar to that of the solar system comets. Why then is the three-eyed Atlas so dry? One explanation relates to temperature. If it formed in a colder area of its home system, farther from its star than Earth is from our sun, then water ice may have been depleted in the early stages of its existence, while carbon dioxide remained. If he wandered through interstellar space for billions of years, cosmic rays could have altered his surface composition. But there was another chemical anomaly complicating the mystery. Data from a very large telescope in Chile detected nickel atoms in the comet's coma. Nickel is not surprising for comets. Many comets show traces of metals, but the three-eyed Atlas produced nickel in exceptionally large quantities, and critically, it produced nickel without the corresponding amount of iron. In nature, nickel and iron are inseparable, neighbors. They form together during the death of stars, erupt into space during supernovae, and condense into planets and asteroids together. Every type of rock we have ever analyzed in space, every meteorite, every asteroid sample shows nickel and iron in roughly the same proportions. They are chemically similar, binding with similar materials, not separating naturally under normal conditions, except in industrial processes. On Earth, we separate nickel from iron when we need pure nickel for special alloys used for corrosion-resistant coatings in high-temperature applications. Nickel coatings and nickel superalloys are used in jet engines and spacecraft components. Data from a very large telescope showed that the emission of nickel sharply increased as the three-eyed Atlas approached the sun. In just 1 month, from July to August, its production rate increased 25 times. The rapid growth, following a steady law depending on the distance to the sun, suggested that something on the surface was heating up and preferentially releasing nickel. There were natural explanations. Perhaps nickel-carbon compounds, exotic molecules rarely found in space, sublimated from the surface, while iron-containing compounds remained stable, which would be unprecedented but not physically impossible. Or the surface composition was multi-layered, with nickel minerals on top and iron-containing materials below, and only the surface was hot enough to release the metals. An alternative explanation, which made headlines and caused surprise, was that the nickel emission matched what could be expected from technological materials. If the three-eyed Atlas was artificial, if it had a metal shell or structural components, nickel alloys would make sense. Their durable and radiation-resistant materials remain stable over a wide temperature range, exactly what is needed for a probe designed for interstellar travel. However, the assumption that the object could be artificial based on its chemical composition is a bold step, very daring, requiring exceptional evidence, and as long as all observations can be explained, albeit with some difficulties, by natural processes. Strange, of course, but natural. Processes we have not seen before, but that is precisely what makes interstellar objects so interesting. Samples from other planetary systems, places we cannot visit, where conditions could have differed greatly from the formation of our solar system. The debates about whether the elongation was real or an artifact continued, as both sides had arguments that could not be easily dismissed. And beneath it all, understanding was growing. Photographs were just part of the story. Chemistry was also just part of the story. It was equally important what we did not see. Data that should have been published, but wasn't. Observations made by several space agencies that they refused to share. The silence that grew louder with each passing day. Chapter 3. Silence that screams. It's surprising how silence becomes noticeable only when you expect sound. In the age of social media, instant updates, and space agencies competing for public attention, this sounds particularly loud from several organizations at once. Recall the achievements of China. The Chinese National Space Administration has published over 14,000 images from the Mars orbiter, Tianwen-1, since its orbit entry in 2021. Это не просто сырые данные. Это тщательно обработанные и красиво оформленные изображения, выпущенные с сопроводительными пресс-релизами, часто приуроченными к национальным праздникам, чтобы подчеркнуть растущие возможности Китая в космосе. When Tianwen-1 created a global color map of Mars with a resolution of 76 meters per pixel, the images were published within a few days. When the accompanying rover, Jirun, landed on the surface of Mars and began transmitting photographs, China ensured the world saw them immediately. This is not unusual. Space agencies use their successes to justify budgets, inspire a new generation of scientists and engineers, and demonstrate technological superiority. During the Cold War, the space race between the United States and the Soviet Union was as much about propaganda as it was about science. Each satellite launch, every human flight into space, and each moon landing was a statement. We can do this. We are advanced. We are strong. This competition has not ended. It has transformed. Today, China and the United States see each other as rivals in space. The Artemis agreements, the U.S. initiative for lunar exploration, deliberately exclude China. In response, China began collaborating with Russia to plan an international lunar research station. The two powers hardly coordinate their actions. The Wolf Amendment, passed in the USA, prohibits cooperation with China. In 2011, Congress explicitly prohibited NASA from engaging in bilateral cooperation with China without special permission. They do not exchange data, do not collaborate, but compete. When the thrice-inhabited Atlas made its closest approach to Mars, and NASA's and China's orbital probes, Tianwen-1, were in perfect positions for observation, it was expected that both agencies would rush to publish their results. Imagine the headlines. China captures unprecedented images of an interstellar visitor, and NASA offers the clearest view of a mysterious comet. These are scientific achievements that are well received both domestically and internationally, justify funding, and inspire excitement. However, none of the agencies published any materials, no processed images, no preliminary analyses, not even a brief statement about successful observations. NASA pointed to a government shutdown that certainly was real and halted the work of thousands of employees. But this shutdown did not prevent the Perseverance rover from continuing to automatically publish images from its navigation camera. These images are uploaded through systems that operate without human intervention, being part of the mission's data management protocols. If raw images from the navigation camera could still be uploaded, why couldn't the original images from the high-resolution camera be published? Why hasn't China, acting completely independently of American budget policy, released any data from Tianwen-1? The United Arab Emirates added another layer to this mystery. Their probe, HOPE, part of the Emirates Mars mission, was specifically designed to study Mars's atmosphere over days and seasons. It carried 3 instruments, including an Emirati red spectrometer and an Emirati ultraviolet spectrometer. These are the perfect tools for analyzing the coma of a comet, for detecting chemical signatures, for measuring how gases interact with solar radiation, and HOPE had a clear line of sight on the triple-inhabited Atlas during the flybys of October 3rd. The UAE was exceptionally proud of HOPE. This was the first interplanetary mission of the Arab world, arriving at Mars in February 2021. The mission team regularly publishes data, releases updates, and interacts with the public. The UAE Space Agency maintains an active presence on social media. They celebrate their achievements, sharing their scientific data. However, after October 3rd, nothing happened. No images of the thrice-inhabited Atlas, no spectroscopic data, nor mentions of observations beyond a brief statement before the flyby confirming they would observe, as if these events simply did not happen from their point of view, despite months of waiting. The European Space Agency became yet another mystery. Their Mars Express and the ExoMars Trace Gas Orbiter were also positioned for observations. The European Space Agency announced in September that observations would take place from October 1st to 7th. It was specified that Mars Express will use its high-resolution stereo camera and spectrometers, while the orbital probe for studying trace gases will use its color stereo system to capture the surface and a set of its own instruments. These observations were not random. They were planned, coordinated actions involving many teams from various European countries. And then, silence. There were no updates on the observations of the three-eyed Atlas on the European Space Agency's website after the initial announcement. No press releases, preliminary results, or images were provided. For the organization that regularly shares stunning images of Mars and publishes results from its numerous missions, this absence seemed intentional. When observers began to point out this coordinated silence across geopolitical borders, interesting historical parallels emerged. There were moments when rival nations collaborated on matters of mutual interest. A partial treaty banning nuclear tests, signed by the United States, the Soviet Union, and the United Kingdom during the height of the Cold War, recognized that atmospheric nuclear tests threaten everyone, regardless of political ideology. This was followed by agreements on space rescue. The Apollo-Soyuz project in 1975 was an example of American and Soviet spacecraft docking in orbit, with crews shaking hands in space despite the ideological confrontation of their countries on Earth. The common denominator was the existing existential threats. When something threatens everyone equally or affects the entire human race, competition becomes secondary to survival or understanding. In 1998, the United Nations Office for Outer Space Affairs developed recommendations, although not mandatory, on how countries should respond to the discovery of extraterrestrial intelligence. These protocols emphasize that no nation should make unilateral statements. Everything must be verified. The international community must be informed. Premature disclosure of information may cause panic, disinformation, or international incidents. If, and this is a significant if, the Martian orbital apparatus has indeed recorded something that calls into question the assumption that the three-eyed atlas is a natural object. A scenario can be constructed where coordinated silence makes sense not as a conspiracy, but as a protocol. Caution, an attempt to confirm results before making statements that cannot be retracted. But for this, one must believe that something unusual has been recorded. And, as the saying goes, extraordinary claims require extraordinary evidence. Silence itself is not proof of anything other than that the images have not been published. There may be mundane explanations. Data processing takes time. Quality control requires careful study. Scientists prefer to publish results in scientific journals rather than through press releases to maintain their reputation and priority of discovery. Government closures, even partial ones, disrupt work processes and delay publications. Nevertheless, this pattern remained alarming. 5 space agencies representing the United States, Europe, China, and the United Arab Emirates all have active missions on Mars and found themselves in a position to observe the same event. However, they decided not to share the results in the first minutes and hours after it occurred. These 5 agencies, usually uncoordinated and competing for prestige and funding, unexpectedly found unity in their silence. Online communities began actively monitoring the situation. On Reddit forums dedicated to space and astronomy, numerous comments have accumulated analyzing every detail. Users noted that the Tianwen-1 mission typically published images within 48 to 72 hours after they were received. They pointed out that the European Space Agency shared images from Mars Express just days after capture, as in previous cases. They also noted that the HOPE mission of the United Arab Emirates has an open data portal created for transparency. Someone noticed that on October 1st, just 2 days before the flybys, the Chinese mission Tianwen-2, a completely different spacecraft heading for samples from an asteroid, released a selfie with Earth in the background. It was a propaganda image, beautifully composed, depicting the Chinese flag on a spacecraft with our planet in the background. The timing seemed significant to the observers. China could very well have published images from space at the moment when observations from the Tri-Eye Atlas were supposed to be processed. They chose to release the image of Tianwen-2 and did not release the observations of Tianwen-1 regarding the interstellar visitor. Did it matter? Or are these just random coincidences that hold no significance? Silence bred theories. Some suggested that all agencies found nothing remarkable, that the Three-Eye Atlas looked exactly as expected, like a comet, and therefore there was no need to rush the publication of results when complete scientific papers could be written. But this did not explain why China did not even use ordinary observations to enhance its prestige. Others suggested theories of technical failures, assuming that all instruments could have malfunctioned simultaneously, but the likelihood of this seemed extremely low. More provocative theories suggested a deliberate suppression of information, that high-quality images could reveal structures and geometries that could not easily be explained as natural phenomena, and spectrographic data could show chemical signatures incompatible with known comets. Numerous agencies realized they were observing something that required coordination for a proper announcement, if it would be announced at all. A blogger compiled a timeline showing that within 72 hours after October 3rd, various government officials and scientists appeared on news programs discussing the Tri-Eye Atlas. Harvey Leb was invited to Newsmax, where he shared the screen with Congressman Tim Burchett, a member of the House Oversight and Accountability Committee. In another news segment, Stephen Miller, Deputy Chief of Staff for Policy at the White House, was directly asked if the president had been informed about the Tri-Eye Atlas. Miller's response was diplomatic and vague, reassuring the public that the relevant agencies were monitoring the situation, but not providing specific information about briefings or conclusions. The fact that White House officials were even asked about the celestial object, that it reached the level of presidential briefings, indicated the seriousness of the situation beyond mere scientific interest. The fact that a congressman was speaking on television about this issue, that questions about the Tri-Eye Atlas were being posed to White House staff, and that the media was covering it as a developing story rather than just a scientific curiosity, all indicated an event that surpassed ordinary astronomical observations. Nevertheless, the main data remained locked. Risky images capable of resolving details the size of 30 kilometers at a distance of 3 atlas during the next close approach could reveal whether the brightness emanates from a massive core or something else. They could reveal the true structure, if such existed. These images could resolve or intensify disputes about elongation, shape, and what this object is in its essence. These images existed. They were captured. Somewhere in NASA's databases, on servers that survived a shutdown, were the highest resolution photographs of an interstellar object ever captured by human instruments, either processed or awaiting processing. And no one had shown them to the world. Silence continued. Days passed. October 6th, 7th. Speculations grew in the vacuum, and while the world awaited official images that never arrived, another peculiarity of the Tri-Eye Atlas began to attract attention. Something noticeable in the observations of enthusiasts made before the object disappeared behind the sun from Earth's perspective, adding another layer of mystery to the already intriguing object. He changed color from red to green, and no one could explain why. Chapter 4. The Green Glow and the Mystery. Color in astronomy is information. When an object in space appears red, blue, green, or any other shade, it indicates its composition, temperature, and the processes occurring on or around it. Sunlight is white and contains all visible wavelengths. When this white light hits a comet, some wavelengths are absorbed by molecules in the coma, while others are re-emitted through fluorescence. The color you see is a chemical trace of what is there. Green comets are not so rare. Many comets acquire a greenish glow as they approach the sun, and the reason for this is well known. A molecule called diatomic carbon, written as C2, forms when larger carbon-containing molecules in the coma are broken down by ultraviolet sunlight. This C2 molecule absorbs ultraviolet light and re-emits it at specific wavelengths in the green part of the spectrum, around 510 nanometers. This process is mesmerizing and so common that astronomers expect to observe it in active comets containing carbon materials. The Tri-Eye Atlas comet was actively observed in July and early August. During this time, it appeared reddish, indicating the presence of dust particles reflecting sunlight with a slight predominance of long wavelengths. It made sense for a comet far from the sun, where sublimation was minimal, and the coma mainly consisted of dust particles slowly released from the warming nucleus. The red color indicated dust. Normal, expected. Then came September 7, 2025, when a total lunar eclipse was observed in some places on Earth, including Namibia. During a total lunar eclipse, the moon moves into the Earth's shadow and the sky becomes darker than usual on a full moon night. This creates perfect conditions for observing faint objects without the bright moonlight washing them out. It's a gift for astronomers. Several hours of dark sky, without waiting for the new moon. Two experienced astrophotographers, Michael Yeager and Gerald Riemann, were in Namibia with equipment aimed at the Tri-Alpha Atlas, both having photographed comets for decades and knowing what to expect in terms of their behavior and colors at different distances from the sun. Their telescopes tracked Tri-Eye Atlas across the sky, compensating for the Earth's rotation and the comet's motion to keep it centered in long exposures. When they processed their images, something changed. Tri-Eye Atlas no longer looked red. It glowed with a green color, a distinctly emerald shade that stretched across the sky for about 2.5 angular minutes in width. The change was dramatic and ambiguous, from one color to another in just a few weeks. The hunter published images online with a caption noting a greenish to bluish-green gas cloud. He mentioned that a faint comet was also visible in the photographs from September 9th. The astronomical community immediately noticed this. The change in color from red to green indicated that the comet's activity had increased, with gases now predominating in the coma instead of just dust. This signaled that Tri-I Atlas had entered a more active phase as solar heating intensified. But here is where everything becomes strange. When the scientists studied the spectroscopic data, a detailed analysis of the wavelengths emitted, they could not find significant amounts of diatomic carbon. Several groups received the spectra of Tri-I Atlas at the end of August and early September, using professional telescopes. The work published by Luis Salazar Manzano and colleagues from the University of Michigan specifically addressed this issue. They discovered an extremely low C2 to CN ratio in cyanogen, so low that they concluded that Tri-I Atlas was one of the most carbon chain depleted comets ever observed. Allow this to be realized. The comet appeared green, which strongly indicated the fluorescence of diatomic carbon. However, spectroscopic analysis showed that the molecule responsible for this green light was actually absent. It feels like seeing smoke without fire, hearing a bell that does not ring. The effect was present, but the cause remained elusive. Several explanations were suggested, one related to the time and place of observation. Perhaps the C2 molecule was in small quantities, but the green glow was efficient enough to be visible even with depleted C2 supplies. The efficiency of fluorescence can vary. A small amount of highly effective fluorescent substance can create a noticeable glow. Another option explained that various molecules can emit green or bluish-green light. Although C2 is most often the culprit, there are other molecules that can fluoresce at similar wavelengths. The task is to determine which molecules are suitable, as they must be plausible for the comet's environment and react appropriately to ultraviolet radiation. Here, cyanide comes into play, not the poison you see in detective novels, although it is chemically related. Cyanogen, or CN, is a radical formed from carbon and nitrogen. It is common in comets. When CN absorbs ultraviolet light, it can emit in the purple and blue parts of the spectrum. Avalab, analyzing the same data that showed extreme nickel production, noted that cyanide production from Comet 3I Atlas sharply increased as it approached the Sun. The speed followed a steady law, increasing with heliocentric distance to the power of minus 9.38. This is an incredibly steep dependence, much steeper than typical comets. Could cyanogen be responsible for the green color? Perhaps. Emission bands of CN indeed extend into bluish-green wavelengths under certain conditions. If CN was in unusually high concentrations, and if dust scattering and other factors contributed to color perception, then the combination could create an observable green tint without the need for large amounts of C2. However, this explanation requires that the 3I Atlas had very unusual chemistry, not just exhausted in carbon chains but simultaneously enriched with molecules containing nitrogen, such as CN. Why would an interstellar comet have such a special combination? What processes during its formation or billions of years wandering through the galaxy could create such an asymmetric composition? Natural comets from our solar system display a variety of compositions depending on their formation location. Comets from the Oort cloud, a distant spherical shell of icy bodies surrounding the solar system, tend to have different ratios of volatile substances compared to comets from the Kuiper belt, a flattened disk of objects beyond Neptune. These differences are related to the temperature during formation, how much processing they underwent from solar radiation, and whether they made previous passes near the Sun. But 3 and Atlas did not form in our solar system. It emerged somewhere else, around another star, in conditions we can only speculate. Perhaps in its home system there were different elemental abundances. Stars form from clouds of gas that are not perfectly mixed. Some regions of the galaxy contain more specific elements than others, depending on the history of supernovae that enriched these areas. A star forming in a nitrogen-rich environment may produce comets with unusual nitrogen and carbon ratios. For example, the comet 3 Eyes of Atlas may be ancient. Considering its speed and trajectory, it is estimated to be between 7 and 14 billion years old, possibly twice the age of our Sun. If this is really the case, then it could have formed during a period that astronomers call cosmic noon, when star formation in the Milky Way peaked. The conditions at that time were different: more supernovae, more radiation, denser stellar environments. Perhaps the comets of that era differ in composition from those formed today. These are reasonable assumptions based on astrophysics, our understanding of stellar evolution, and galactic history. They allow the comet 3 Eyes of Atlas to remain a natural object despite its peculiarities. However, there is another point of view that lingers in the mind. If you were designing a probe for interstellar travel, what would you use as fuel? Chemical rockets are inefficient for interstellar distances. Something more exotic would be required. Perhaps highly efficient engines ejecting particles at extremely high speeds. Or, if you want to be clever, you could use solar energy by passing close to stars, sublimating volatile substances for thrust, using the star's radiation to adjust your trajectory. If you wanted your probe to look like a comet to any observers, you could cover it with ice, with volatile substances that would predictably sublimate when approaching the star. Dry ice would be a sensible choice. It is stable at very low temperatures, abundant in space, and sublimates actively when heated. If you needed to create thrust for small maneuvers, controlled sublimation of carbon dioxide from specific vents could help. If your probe used nitrogen propellants or cooling fluids, leaks or intentional emissions could lead to the formation of cyanogen due to the interaction of these substances with solar radiation. This speculation is important to emphasize that there is no direct evidence that the 3-eyed Atlas comet is artificial. Nevertheless, chemical anomalies, depletion of carbon chains alongside sharp production of cyanogen, and the appearance of a greenish color without the expected molecules create a pattern that is difficult to fit into standard comet models. An astronomer, wishing to remain unnamed, noted in a conversation with a science journalist that if one were to list all observations of the comet 3 Eyes of Atlas and ask how many could be easily explained by natural processes of comets, the answer would be mixed. Some moments are suitable. Active comets emit gas, forming comas, and sometimes display unexpected chemical properties. But when you look at all the observations as a whole, the overall likelihood of all these anomalies in one natural object begins to cause discomfort. This is a task related to Bayesian statistics. Each individual deviation may be unlikely, but possible. Low C2 green is rare, but it could be CN or something else. Nickel without iron seems strange, but perhaps it's the result of some exotic chemical process. The prevalence of carbon dioxide is unusual for comets we know, but not impossible for an object from another system, and its elongated shape could be either an imaging artifact or a manifestation of unusual geometry. But if you multiply the probabilities, if each anomalous event has a 10% chance of natural origin, and you observe 7 independent anomalies, then the total probability is 0.1 to the 7th power, which equals 1 in 10 million. However, anomalies may not be completely independent. Some of them may be interconnected and share common causes, while individual probabilities are largely assumptions. We do not have enough examples of interstellar objects to calculate real statistics. Nevertheless, this task illustrates why some scientists began to feel that seeking natural explanations for everything regarding the 3-eyed Atlas requires stretching plausibility, but not breaking it. The green glow gradually faded over the following weeks as the 3-eyed Atlas approached the sun and eventually disappeared from Earth's view behind the solar brilliance. By the end of September, observations from Earth became impossible. The object was too close to the position of the sun in the sky, lost in the dazzling light. It remained invisible from Earth until early December, when it appeared from the other side of the sun, completing its perihelion passage. This meant that the flyby past Mars on October 3rd was one of the last opportunities to study the 3-eyed Atlas before it reached its most active phase near perihelion. And when these observations remained unpublished, when the silence from the space agencies continued, the green mystery became yet another piece of the puzzle that did not resolve into a clear picture. What is a 3-eyed Atlas? A chemically strange natural comet with an unlikely but possible set of properties, or something that merely resembles a comet while remaining fundamentally different? The answer, as many believed, lay in a metallic signature that continued to strengthen in the production of nickel that defied simple explanation, and perhaps most disturbingly, in how this nickel was released, as if something were activated rather than passively sublimated. Chapter 5. Industrial Alloys. From deep space, a very large telescope in Chile is not a single instrument, but an array of 4 massive telescopes, each with a main mirror element measuring 8.2 meters in diameter. When they work together through interferometry, they can achieve a resolution equivalent to a telescope with a diameter of over 100 meters. This is one of the most powerful ground-based observatories in the world, operated by the European Southern Observatory, and it has been observing a three-eyed atlas since July. The light spectrum of ultraviolet and visible range obtained using the UVA spectrograph particularly effectively reveals weak emission lines of metals. When atoms of elements like iron, nickel, sodium, or calcium are in a comet's shell and exposed to ultraviolet radiation from the sun, they emit light at very specific wavelengths. These emission lines can be compared to fingerprints. Each element produces a unique pattern, and the intensity of these lines indicates the amount of the emitted element. A team observing the Comet 3I Atlas with a UVA spectrograph, including Rohan Rahat Gundar and his colleagues, was specifically searching for metallic emissions, as previous observations had shown that their detection is possible, but challenging. The temperatures in most comets are too low for the sublimation of minerals containing these elements. Typically, temperatures above 1000 Kelvin are required for the sublimation of silicate or metallic particles. Most comets, even active ones, do not reach such temperatures until they come extremely close to the sun. Nevertheless, Comet Tri-I emitted metallic emissions while being more than 3 astronomical units from the sun, which is 3 times the distance from Earth to the sun. At such a distance, solar heat is not intense enough. The intensity of sunlight decreases with the square of the distance. 3 times farther means that solar energy per square meter becomes 9 times less. Ideally, it should be too cold for metal sublimation. Yet, they were still present. The emission lines of nickel were clear and unmistakable, and as Comet Tri-I approached the sun, these lines not only gradually intensified, they exploded. From late July to late August, as the distance changed from about 3.9 astronomical units to 3.1, the production speed of nickel increased 25 times. 25 times more nickel per second in just 1 month. The team modeled this increase and discovered that it follows a power law. The production rate depended on the heliocentric distance raised to the power of minus 8.43, with an error of 0.79. This is an extremely steep dependence. In comparison, most comet emissions depend on the distance raised to the power of minus 2 to minus 4. Water sublimation typically follows an inverse square relationship, minus 2, because it is driven by solar heating, which itself obeys the inverse square law. A temperature of minus 8.4 means that the production speed is very sensitive to distance. If you get even a little closer to the sun, the emission speed increases sharply. This is not a smooth increase. It is explosive. And this pattern does not correspond to simple thermal sublimation of surface ice. Then the problem arises with iron, or more precisely, the problem of the absence of iron. The same observations using UVA spectrograph, which recorded the emission of nickel, also searched for iron emission lines. Iron must be present. In every meteorite, in every asteroid, in every sample of cosmic material ever analyzed, nickel and iron are found together. The ratio may vary slightly depending on the specific mineral, but both are always present. In the initial observations of the Comet Tri-I Atlas, no iron was detected at all. When the comet approached closer and the nickel signal intensified, iron finally appeared, but only when Tri-I Atlas was at a distance of 2.64 astronomical units from the sun. Even then, the ratio of nickel to iron turned out to be extremely unusual, much higher than that of any comet in the solar system or the previous interstellar comet. The authors of the study described it as a highly mysterious phenomenon. This is a scientific understatement. When researchers use phrases like extremely mysterious or unprecedented in peer-reviewed articles, they signal that they have exhausted traditional explanations and are entering a realm where new physics or chemistry may be needed. Why does nickel separate from iron? We know how to do this in industry. The Mond process, developed in the 19th century, uses carbon monoxide to form nickel carbonyl, a volatile compound that can be separated from iron. For this, the ore is heated with carbon monoxide at moderate temperatures. Nickel reacts, forming nickel carbonyl gas, which boils at 43 degrees Celsius. The gas is collected and then heated to higher temperatures, where it decomposes back into pure nickel and carbon monoxide. The carbon monoxide is processed, resulting in refined nickel. Thus, we obtain high-purity nickel for electronics and corrosion-resistant alloys with a nickel coating that protects steel components. Industrial chemistry refined over more than a century. a standard in metallurgy textbooks. And it seems this is happening at Tri-I Atlas. The alternative requires addressing nickel carbonyl through processes we have never observed in comets. If the comet contains nickel minerals and carbon monoxide, which we know it has in abundance, then solar radiation could potentially lead to reactions forming nickel carbonyl. This compound is volatile enough to sublimate at relatively low temperatures, much lower than those required for the evaporation of metallic nickel or nickel silicates. Iron can remain bound in various minerals that do not form similar volatile compounds under the same conditions. Iron carbonyl exists, but requires different conditions for formation. If the mineralogy of Tri-I Atlas is such that nickel is preferably available in forms capable of reacting with carbon monoxide, while iron is locked in more stable compounds, theoretically observable separation can be achieved. But this requires many conditions. A very specific mineralogical composition is needed, different from anything we have seen in the comets of the solar system. Conditions are required that preferably form nickel carbonyl while suppressing the formation of iron carbonyl. It is necessary for these exotic conditions to be sufficiently common for an interstellar comet to naturally exhibit them, despite interstellar comets being incredibly rare, and this being only the third one we have discovered. The alternative is that the nickel signal does not arise from natural sublimation, but occurs from a surface artificially created. Nickel is widely used in the construction of spacecraft. Nickel alloys are preferred for components exposed to radiation, extreme temperatures, and corrosive environments. Fuel tanks are often coated with nickel. Structural elements and satellites use nickel alloys with steel or titanium. Even spacecraft like rovers employ nickel in wheel mechanisms and electronic shielding. If Tri-I Atlas were artificial, if it had a metallic body or frame, solar heating when approaching the sun would cause gases to be released from its surface. Any volatile compounds on the surface, including those used for thermal regulation or as protective layers, would sublimate. If the structure used nickel alloys, which makes sense for an interstellar probe needing strength and radiation resistance, one could expect nickel to be released. This release would follow a steep power law if it were caused by a threshold effect. Imagine a probe covered with a layer of insulating material, possibly ice accumulated over billions of years in interstellar space. As solar heating increases, the outer layers sublimate, but the metallic structure beneath remains protected. Then, upon reaching a certain temperature threshold, the insulating layer becomes thin enough for heat to reach the metal surface. Once this happens, the metal itself begins to heat up rapidly, and any volatile compounds associated with it start to evaporate. This transition will be sharp. Below the threshold, minimal emission. Above, a rapid increase in emission as heating and exposure of the metal surface increase. A steep degree of dependence on emission naturally arises from such a threshold-activated process. Is it really so? It's impossible to know for sure without additional data, but the observed pattern corresponds to activation rather than passive thermal sublimation. It seems like something that turns on, rather than something that gradually heats up. Other metals were also studied in the spectra. Sodium, which is often found in many comets of the solar system and produces bright yellow emission lines, was not detected in significant amounts. Calcium, another metal sometimes found in comets, was also absent. It was nickel with its characteristic green emission lines that dominated the metallic spectrum. The mystery of temperature deepened as researchers calculated the surface temperatures needed to explain the observations. Even at a distance of 2.1 astronomical units, Tri-I Atlas must have a surface temperature of only around 200 kelvins. This is significantly lower than the approximately 1,000 kelvins needed for the sublimation of silicate minerals, yet nickel was being effectively released. Either the surface of the comet was significantly hotter than simple thermal models predicted, possibly due to some exotic greenhouse effect or an underground heat source, or nickel was released not from direct sublimation of minerals, but as a result of some other process. The formation of nickel carbon monoxide occurs at lower temperatures, making it a preferred natural explanation. However, its formation requires a suitable chemical environment, corresponding minerals, and the right proportions of reagents. There is one more detail that caught attention. The production of cyanogen was increasing even faster than nickel. The rate of cyan emission depended on the distance by -9.38. If you use natural chemistry to explain both nickel and cyanide, you need the process occurring to produce both substances in rapidly increasing amounts with slightly differing but constant steep dependencies on the distance from the sun. Cyanide is, of course, toxic to life on Earth in most of its forms. Hydrogen cyanide, known as HCN, is used in chemical weapons and executions, but the CN radical, cyanogen, is different. It often forms from ammonia or other nitrogen-containing molecules when they break down under ultraviolet light. The search for CN in a comet is not surprising, but its discovery with observed production rates and such a steep dependence on distance is indeed interesting. If nickel and cyanide are combined, both increase sharply, following the laws of degree that suggest threshold effects or activation, rather than simple thermal sublimation, and both facts are difficult to explain from the perspective of traditional cometary chemistry. What is also noteworthy are the molecules that have industrial or technological significance. Nickel is used in alloys and coatings, cyanide compounds in chemical synthesis and material processing. Is this a coincidence? Are we observing natural processes that accidentally resemble what we expect from technology? Or are we seeing technological signatures created with a specific purpose beyond mere random gas emissions? Observations could not provide a definitive answer to this question, but they intensified the feeling that the three-eyed atlas is unlike any comet humanity has ever studied. With the approach of perihelion on October 29th, when the comet reaches its closest point to the Sun at just 1.36 astronomical units away, the metal ejection will reach maximum intensity. If the patterns had persisted, if the laws of degree had continued to lead to a logical conclusion, nickel production would have increased by additional orders of magnitude in recent weeks. This moment, when solar heating reaches its peak and gas emission is at its highest intensity, will be crucial. Will the three Atlas moons behave like a comet, pushed to its limits, possibly breaking apart or producing a spectacular eruption? Or will it behave like something powered by solar energy for movement or trajectory adjustment? For purposes we can only guess. The metallic signature is a clue, but like all clues in this strange matter, it points in several directions, refusing to resolve into certainty. While scientists argued about nickel-carbon and alloys for spacecraft, another group of anomalies demanded attention. The trajectory followed by 3I Atlas through the solar system revealed its own peculiarities, mathematical improbabilities that question the limits of coincidences. Chapter 6. 7. Impossible Things Before Perihelion. Avi Loeb became a polarizing figure in astronomy. To his supporters, he is a rare scholar willing to challenge orthodox thinking, ask uncomfortable questions, and explore possibilities that others dismiss without thought. For his critics, he resorts to extraordinary explanations too quickly when ordinary ones would suffice, too eager for media attention, too prone to publish provocative ideas before they are thoroughly vetted by the community. However, his achievements are undeniable. He was the former chair of the astronomy department at Harvard, founder of the Black Hole Initiative, author of over 800 published articles, and recipient of awards from institutions worldwide. When he speaks about astrophysics, people listen, even if they disagree. In early October, on the day when the 3I Atlas came closest to Mars, Loeb published a summary of what he called the 7 anomalies of this interstellar visitor. Some of them have already been mentioned, but understanding them as a whole, realizing how they are interconnected and enhance each other, is where the true significance of the mystery becomes apparent. The first anomaly concerns size and mass. When the 3I Atlas was discovered in July, astronomers measured its brightness and tried to determine what it should be. If we assume that the object reflects about 5% of the sunlight that strikes it, a typical albedo for asteroids and comet nuclei, then the brightness observed from Earth implies a diameter of about 20 kilometers. 20 kilometers is a huge size for an interstellar object. Oumuamua was estimated to be about 100 meters long, roughly the length of a football field. 2I's, or Borisov, the second interstellar visitor, had a diameter of about 1 kilometer. Now, there was 3I Atlas, potentially 20 times larger than Borisov and 200 times larger than Oumuamua. The problem with large interstellar objects is that they must be exceptionally rare. Two systems do not easily eject their large members. When planets form and gravitational interactions break apart objects in orbits, it is the smaller bodies that are ejected. The larger the object, the greater the gravitational energy binding it to its home system, making it harder to achieve escape velocity. It was expected that interstellar space would mainly be populated by small debris, with larger objects becoming exponentially rarer as size increases. A trial calculation showed that if the 3-eye atlas indeed has a diameter of 20 kilometers, its detection over 5 years of continuous sky observation implies the existence of interstellar objects, which is impossible. The Milky Way must produce and eject objects on a scale that significantly exceeds the metrics that allow for the formation of stars and planetary systems. This would require almost every star system to eject massive planetesimals, which contradicts everything we know about planetary dynamics. An alternative option is that the object is not 20 kilometers of solid rock. Most of the brightness comes from a vast coma of dust and gas, while a much smaller core is hidden inside. It would make sense for the comet, and would allow the mass to be reduced to acceptable levels, but then it is necessary to explain why this comet exhibits all other anomalies, why its chemical composition is so strange, and why it produces metals at impossible rates. The second anomaly is related to the front jet. When the Hubble telescope captured an image of the triple comet Atlas on July 21st, the photographs revealed something unusual. The scattered sunlight seemed to stretch towards the sun rather than away from it. Comets develop tails that point away from the sun because radiation pressure and solar wind push gas and dust outward. The tail always points generally in the direction opposite the sun, like a flag showing the direction of the solar wind. But with the triple comet Atlas, the opposite was observed. The solar glow stretched forward, which astronomers call an anti-tail. Liob and his colleague Eric Cato carefully analyzed the Hubble image and determined that the glow extended about 10 times further towards the sun than perpendicular or away from it. Considering the geometry of observation and the angle from which Hubble conducted his observations, this ratio becomes even more extreme. Anti-tails are not entirely unknown. Some comets develop them due to specific geometric effects, where dust particles ejected earlier in the orbit remain in the plane of the comet's orbit and appear to be directed forward when viewed from certain angles. But such phenomena are usually temporary, appearing and disappearing with changes in the geometry of observation, and typically do not display the extreme elongation demonstrated by the triple comet Atlas. The front jet may indicate active substance emission from the sunlit side of the core. If volatile substances sublimate mainly from the hemisphere facing the sun and are ejected with sufficient speed to temporarily overcome radiation pressure, a jet directed towards the sun may form. However, this requires very specific conditions and active emission, and it still does not explain the extreme elongation or permanence of this phenomenon during multiple observations. The third, fourth, fifth, and sixth anomalies are related to the trajectory, and here the statistics become uncomfortable. The triple comet Atlas entered the solar system on a retrograde orbit, moving in the opposite direction of the planets around the sun. Her orbital plane is tilted about 5 degrees relative to the ecliptic, the plane in which Earth and most planets revolve. 5 degrees may not seem much, but space is a three-dimensional expanse. If interstellar objects can appear from any direction, which makes sense since there are no reasons for them to approach at any specific angle, then the probability that the object's orbit will be within 5 degrees of the ecliptic plane is about 0.2%, or 1 in 500. It's not impossible, but unlikely. If the three-eyed Atlas arrived by chance, one might expect it to appear from any direction with equal probability. The plane of the ecliptic is important to us, to our solar system, because that's where the planets are. But in interstellar space, it doesn't have much significance. So why is this interstellar guest aligned with her? Now let's consider the close approaches. The three-eyed Atlas passed within 29 million kilometers of Mars on October 3rd. It will also pass near Venus. Its trajectory will bring it quite close to Jupiter in March 2026. These distances are not impacts or even particularly close flybys by cosmic standards, but they are closer than statistically expected for a random trajectory. Scientists calculated the probability that an interstellar object entering the solar system on a random trajectory would come close to several planets. The answer depends on how you define nearby, but using reasonable definitions of proximity, the cumulative probability is about 0.005%, or 1 in 20,000. Again, this is not impossible. Unlikely things happen. Lottery winners exist despite odds of millions to 1, but you start to ponder when unlikely events begin to accumulate. Time also matters. Planets rotate at different speeds. Mars takes about 687 days to complete one orbit, Jupiter nearly 12 years, and Venus 225 days. The likelihood that an interstellar object arrives not only on a trajectory passing near 3 planets, but also at moments when each planet is in the right place in its orbit for a close approach, multiplies the already low probability of the trajectory by yet another factor. A rough estimate of the combined probability of both the trajectory and timing is about 1 in 200,000. You layer unlikely events on top of each other. The seventh anomaly may be the most speculative, but also the most intriguing. The arrival direction of the three-eyed atlas, when traced back through interstellar space, points to a region of the sky near the constellation Sagittarius. It is not surprising in itself, as the archer is directed towards the center of the galaxy, an area rich in stars, but scientists have noticed that this direction is within 9 degrees of another known signal from this region. On August 15, 1977, the Big Ear radio telescope in Ohio detected a strong narrowband radio signal that lasted 72 seconds. The signal was at the same frequency that neutral hydrogen naturally emits. This frequency is considered a reasonable choice for interstellar communication, as any technologically advanced civilization would be familiar with it. The signal was so unusual and seemed so artificial in nature that astronomer Jerry Amon wrote, "Wow," next to it on the printout. And since then, this signal has been known as the WOW signal. Despite numerous attempts, the signal was never recorded again. Explanations range from terrestrial interference to a passing comet that somehow could have created a signal at the right frequency, and yes, possibly an extraterrestrial transmission. The mystery remains unsolved nearly 50 years later. Does this mean anything that the trajectory of the three-eyed atlas, if traced back, points to an area 9 degrees from the source of the WOW signal? Bob calculated the probability of this coincidence to be about 0.6%, which is better than some other coincidences, but still unlikely. But here's the question. If you are an extraterrestrial civilization sending a probe to a solar system, possibly discovered through radio transmissions or observing planets passing in front of their star, how would you announce your arrival? You could first send a radio signal, a kind of greeting message. Then, if you want to send a physical probe, you could direct it along the same trajectory from the same place, so that anyone connecting the dots would understand that the signal and the probe are related. This is speculative. Linking the three-eyed atlas with the WOW signal requires faith that both are artificial and interconnected, which goes beyond the data. But alignment exists, it can be documented, and it adds another layer to an already complex picture. When you list all the anomalies, 7 of them create a cumulative weight. A large size for an interstellar object, behavior contrary to normal comet behavior, an extreme chemical composition with nickel without iron and a predominance of carbon dioxide, a green color without molecules that should cause it, a trajectory aligned with the ecliptic, arrival time optimized for passing by planets, and an arrival direction coinciding with a historical, anomalous radio signal. Each anomaly has possible natural explanations, sometimes strained, requiring special conditions or poorly understood chemistry, yet they are explanations. Science works to find natural explanations for observations. Only when natural explanations become more strained and unlikely than artificial ones do you have to seriously consider the latter. This threshold is subjective. It depends on your previous beliefs about the likelihood of artificial explanations. If you believe that the probability of encountering alien technology in our solar system is virtually zero, then no amount of anomalies will convince you. You will always lean towards even the most unlikely natural explanations, as they are still more likely than aliens. However, if you allow even a small chance that interstellar probes may exist and occasionally pass through our solar system, then every anomaly increases that probability. If there are several such anomalies, the initially very small probability becomes less small. It may still be insignificant, but it can no longer be dismissed. Loeb clearly articulated his thoughts on this matter, repeatedly asserting that the three-body atlas is likely a natural comet. But he insists that the possibility of its artificial origin should be seriously investigated. In his view, we must gather as much data as possible, use our best tools, direct radio telescopes at the object, analyze every spectrum, and track any deviations from purely gravitational motion. Because if even 1% probability, even 0.1%, indicates that we are witnessing the flight of a probe from another civilization, then the consequences are so significant that we must thoroughly investigate the situation. The cost of error is small. We observe an unusual comet and learn something about interstellar chemistry. However, if we ignore the possibility of artificial origin, we will miss the first contact. Such reasoning divides the scientific community. Some see it as prudent caution and open inquiry, while others view it as sensationalism and a lowering of evidential standards in pursuit of unlikely scenarios. Debates reflect deeper questions about how science should perceive truly anomalous observations, how we balance skepticism with curiosity, and how we decide when something is strange enough to deserve exceptional attention. And all of this, 7 anomalies and debates about their meaning, will reach a critical point on October 29th, when 3 Atlas IAs will pass perihelion and encounter the full impact of solar radiation on their closest approach to the Sun. Chapter 7. What Politicians Know. In Washington, there is a peculiar protocol when scientific issues intersect with national security. Everyone goes through channels that the public never sees. Intelligence briefings happen behind closed doors. Congressmen with access to classified information receive updates that don't make it to press releases. And sometimes carefully chosen words in public statements reveal that people in high positions know more than they say. Questions began to arise on October 2nd, the day before 3 spacecraft would reach their closest approach to Mars. Stephen Miller, acting Deputy Chief of Staff for Policy at the White House, was giving interviews on news programs discussing the government shutdown. Typical appearances explaining budget negotiations and operational continuity. But then, in one of the programs, the journalist asked a question that seemed to surprise Miller a bit. Did the president receive a briefing regarding the 3 AI Atlas? Miller's response was measured and thoughtful. He confirmed that the relevant agencies are monitoring the situation. He reassured, assuring of the scientific competence and thoroughness of the conducted research. He emphasized that the Earth is not in danger, and the object will pass far from our planet. However, he did not answer whether the president was informed about this. He neither confirmed nor denied this fact. Instead, he switched to discussing the possibilities of American space programs and the importance of further investments in NASA. This shift in response was informative in itself. If the object called the Three-Eyed Atlas turned out to be just an interesting astronomical phenomenon, a natural comet, the answer would be simple. No, the president was not informed about specific astronomical observations. Thousands of astronomers make discoveries every day. Presentations for the president concern issues of national importance, security threats, diplomatic crises. A comet, however unusual, usually does not rise to such a level. But Miller did not say this. He did not dismiss the questions as absurd. Instead, he took them seriously, speaking about monitoring in a way that implied ongoing attention from federal agencies. This choice of words, the reluctance to simply say no, all hinted that Three-Eyed Atlas had indeed reached the levels of government where decisions about information management are made. At the same time, Representative Tim Burchett from Tennessee appeared on Newsmax. Burchett is a member of the House Oversight and Accountability Committee, which oversees federal agencies, including NASA. He actively advocates for transparency, especially regarding unidentified aerial phenomena, insisting on the declassification of government files and public disclosure of what agencies know about unexplained objects. Burchett appeared on screen alongside Avia Loeb, and both discussed the Three-Eyed Atlas and its anomalies. This combination was significant in itself. Members of Congress usually do not share airtime with astrophysicists to discuss current scientific observations. They give interviews on legislation, politics, and political disputes. Communication of science is typically handled by scientists and educators. But a member of Congress, in the midst of an active government shutdown, found time to publicly discuss an interstellar object. Burchett spoke about the need for transparency and that the public should have access to information gathered by government-funded missions. He raised it as a principled issue, arguing that NASA data belongs to the American people who paid for it and that there is no justification for concealing observations of a natural phenomenon. The subtext was obvious. Burchett believed that certain information was being concealed, using his platform to pressure agencies, making them feel political discomfort for their silence. Then, Anna Paulina Luna from Florida appeared. The moon seemed to have been informed, in particular, about the elongated images of Perseverance. It directly contacted Avi Loeb, asking him to analyze a photograph capturing a stripe. This is unusual. Members of Congress regularly receive scientific reports, but they usually come from representatives of agencies like NASA or from experts appointed by scientific and technological committees. They typically do not seek independent opinions from university professors. The fact that the moon sought external expert analysis indicates that it was either dissatisfied with the official explanations or did not receive them at all. Both scenarios are concerning. If NASA provided reports that did not properly explain the images, it implies that the agency was either uncertain or evasive. If NASA did not provide any reports despite Congress's interest, it may indicate that information was actively concealed. The moon moved on. She sent a letter to NASA proposing to use the Juno spacecraft, currently in orbit around Jupiter, to study comet 3X Atlas when it passes relatively close to Jupiter in March 2026. The letter emphasized the scientific value, unique opportunity, and importance of maximum observation of interstellar objects, considering their rarity. However, letters from representatives to agency leaders regarding specific scientific missions are not common. The Congress sets budgets and exercises control, but usually does not interfere with which astronomical objects specific spacecraft should study. This is left to the discretion of scientists and expert panels. The moon's letter suggested either exceptional interest from voters, which seems unlikely for a little-known astronomical event, or particular concern based on information that prompted her to personally intervene in the mission planning. Numerous political addresses pointed to something greater. Several Congress members, representing different committees, showed interest in the comet Tri-X Atlas. White House staff were interrogated about presidential briefings, while scientists were invited to share platforms with politicians. This does not happen for typical astronomical discoveries, regardless of their scientific significance. In 2019, when the first image of a black hole was published using the Event Horizon Telescope, it became a sensation in newspapers, a scientific triumph, and the culmination of decades of theoretical work and years of data analysis. However, no member of Congress appeared on television to discuss this. The White House made no statements, and this topic remained a scientific news item covered by science journalists and noted by the astronomical community, but did not rise to the level of political discourse. Or let's take the discovery of phosphine in the atmosphere of Venus in 2020, which briefly gave hope for the existence of microbial life in the clouds of Venus. This became a significant event affecting astrobiology and the search for life beyond Earth. It sparked interest and discussion, but again, without any political involvement, except for routine NASA press releases. The three atlases of view differed from each other, and this difference was essentially an uncertainty, unresolved questions, and the possibility of changing interpretations depending on what the data actually shows. There is a precedent in history worth considering. In 1906, when the first serious proposals for systematic searches for extraterrestrial intelligence emerged, scientists and politicians quietly developed protocols in case an artificial signal was detected. These protocols emphasized the importance of verification, caution, and international coordination before a public announcement. The main assumption was that the unilateral disclosure of information by one nation or institution could incite panic, be misinterpreted, and provoke diplomatic incidents. These protocols are not binding agreements. Their recommendations were developed at seminars and conferences, offering advice on best practices, reflecting a consensus that the discovery of extraterrestrial intelligence is an event of significance for all humanity, with implications beyond science, requiring coordination at the government level. Considering that the data obtained from three gaze atlases was ambiguous enough to potentially indicate artificial origins, it would be prudent for federal agencies to inform selected representatives. Not to confirm the presence of extraterrestrial technology, but to inform them of an unusual situation where there is high public interest and the interpretation of the data remains uncertain. This was necessary to prepare for questions from voters and the media, to coordinate messages so that different agencies did not contradict each other. However, the government shutdown complicated the situation. During normal times, NASA has public relations staff, prepared statements, and coordinated communication strategies. But during a shutdown with minimal staff, this infrastructure collapses. Scientists on leave cannot respond to media inquiries. Press releases are not prepared. Coordination between agencies is disrupted. In this vacuum, individual scientists have started to speak independently, publishing blogs daily. Other astronomers gave interviews to science journalists, while amateur researchers posted analyses on social media. Without centralized coordination, the narrative fragmented, with multiple interpretations circulating simultaneously, none officially supported, all competing for attention. This created political problems. If you are trying to manage information about an uncertain situation, the last thing you need is decentralized communication, where different experts offer conflicting interpretations. It complicates management and makes it difficult to maintain message consistency. This gives rise to conspiracy theories, as the lack of official clarity allows speculation to thrive. Some observers suggested that the closure was planned to prevent coordinated information disclosure. After firing the NASA employees, the administration created a plausible explanation for why the data is not being published. If the scientists are not working, the data is not processed, the websites are not updated, then naturally, silence ensues. This is not suppression, but logistics. Nevertheless, timing coincidences can be real. Government shutdowns occur when budget negotiations stall, caused by political factors unrelated to astronomical events. October 1st coincided with an incident that happened 2 days before the flyby near Mars. The Federation's financial year ends on September 30th. Budget resolutions are either accepted or rejected depending on the voting in Congress and the President's decisions to sign or veto. The trajectory of the comet does not affect this process. Nevertheless, the coincidence troubled people, just as the 7 anomalies in the trajectory and chemistry of the three-eyed atlas accumulated into something that resembled less and less a mere chance. The timing of political silence, technological quiet from several countries, a shutdown that disrupted communication precisely when it was most needed, all of this felt orchestrated, even if it wasn't. Dr. John Brandenburg added another voice to the political dimension. He is a plasma physicist with experience in defense research and runs a website called Blue Planet Red, where he discusses Mars research, including controversial theories about past nuclear events on the planet. He posted a video analyzing a three-eyed atlas, noting statements from the White House and emphasizing that official assurances often precede more detailed disclosures. Brandenburg's track record is ambiguous. He published peer-reviewed articles on plasma physics alongside speculative theories about ancient Martian civilizations, which most scholars dismiss. He occupies that ambiguous niche where legitimate qualifications coexist with marginal theories, but his participation highlighted how the three-eyed atlas attracted attention from diverse circles, from mainstream scholars to those working on the fringes of accepted scientific knowledge. Political interest, questions raised at a high level, unusual coordination needed to explain the silence in several countries, all pointed to the fact that the three-eyed atlas had become something more than just astronomical curiosity. It turned into an event requiring management, decisions on what to say and when, needing briefings and coordination beyond a typical scientific discovery. And this management, this careful control of information could not last forever. Eventually, the observations will be processed, articles will be published, and the data will be made public through review or leaks. Questions demanded answers, and these answers, when they appeared, should have concerned not only what the three-eyed atlas was, but also why a political reaction was needed. Meanwhile, astronomy enthusiasts did not wait for official statements. They had their own telescopes, proprietary software for data processing, and communities for sharing and analyzing information. In the absence of professional releases, amateur observations became the main source of visual information about the three-eyed atlas. Some of these observations raised new questions. Some seemed to show what should not be there, and some were likely artifacts of the image, erroneous interpretations, or the result of unreliable expectations. However, separating the signal from the noise when everyone looks at dull objects through the atmosphere with modest equipment becomes nearly impossible without professional resources capable of providing earthly truth. Chapter 8. The image NASA doesn't want you to see. Amateur astronomy has a rich history of contributing to professional science. Discoveries of supernovae, findings of comets, monitoring of variable stars. All these efforts partially rely on networks of amateur observers with telescopes in their backyards and a dedication to observing the night sky. Around the world, thousands of astronomy enthusiasts possess equipment that was considered professional just a generation ago. Cameras controlled by computers, computerized mounts, complex image processing programs. The boundary between amateur and professional capabilities has blurred significantly. When the three-eyed atlas was discovered, amateur astronomers immediately began tracking it. Coordinates were published online. Predictions were calculated and shared in tables, showing when the object would be visible each night. Observational campaigns were organized through forums and social media groups. People wanted to see this interstellar guest with their own eyes. to capture their own photons reflected from something beyond our solar system. One of the observers used the nickname Dobsonian power, named after Dobsonian telescopes, a popular design among enthusiasts for its simplicity and large aperture. On October 3rd, as the three-eyed Atlas approached Mars at minimal distance, Dobsonian power observed with a solar telescope, equipment designed for safe sun observation, blocking most of its light and allowing certain wavelengths to pass through. Why use a solar telescope to observe a comet? Because the three-eyed Atlas was in the sky near the sun from the Earth's perspective. Not directly in front, but close enough that observation during the day with specialized equipment became necessary. Solar telescopes with narrow filters can detect bright objects near the sun that would be invisible to regular telescopes, overwhelmed by the solar glare. Dobsonian power took a photo and shared it online. The image was heavily processed, enhanced to highlight dull details, and the contrast was pushed to the maximum. On the horizon appeared a controversial, dark, somewhat elongated shape against a light background, grainy and unclear, but undoubtedly displaying some structure. For several hours, the image went viral. Debates and interpretations ignited on social media. Some claimed it was clear evidence of an elongated object, confirming images taken by Perseverance, while others saw only noise, artifacts of aggressive image processing, and a parody of the human tendency to find patterns in random data. Few reminded that solar telescopes are not meant for observing comets and can cause distortions. Professional astronomers quickly expressed skepticism. The image quality was poor, and the processing excessive. Not knowing the exact parameters of the equipment, exposure time, and processing stages, it was impossible to assess what constituted a real signal and what was an artifact. One of the astronomers noted that with overly aggressive image enhancement, anything could be made to appear structured. Sound patterns become signs, while optical aberrations appear as boundaries. The human brain does the rest, connecting the dots into shapes. However, the technical flaws of the image did not prevent it from spreading. News outlets picked it up, and analysis videos appeared on YouTube. Comparisons were made with images of Perseverance, early photographs of Hubble, and artistic interpretations of what an interstellar probe might look like. And, as often happens, images created by artificial intelligence began to appear, supposedly showing what the triangular atlas looks like. Elegant metallic structures with incredible detail, entirely fictional, but presented as enhanced versions or artistic interpretations. The flow of content generated by AI created a second problem: how to distinguish real amateur observations, sincere but imperfect attempts to capture an object, from fictional renders created to attract clicks. Some images created by AI were clearly fake, showing surface details that no telescope could resolve at such distances. But others were more subtle, displaying comet-like structures with enough ambiguity to seem like real photographs. Meanwhile, genuine amateur observations continued. Astrophotographers with tracking mounts and telescopes that automatically compensate for the Earth's rotation to keep objects centered during long exposures obtained better quality images than attempts by the Dobsonian Solar Telescope. Gerald Raymond and Michael Yeager in Namibia have already recorded a change in green color. Other observers in the southern hemisphere, where the triangular atlas was better visible before disappearing behind the sun, were uploading their results to astronomical forums. These images showed something interesting. With proper tracking and shooting using narrowband filters isolating specific emission lines, the triangular atlas appeared to have an elongated white or yellow core surrounded by a green halo. The core appeared elongated in many higher quality images, not dramatically, but noticeably abnormally round. The elongation was not 4:1, like in the case of the Perseverant composite, but resembled more 2:1, or 1:1.5. Was this a real structure or merely an artifact? Telescopes tracking objects compensate for the Earth's rotation, but the comet moves against the backdrop of the stars. If the exposure time is long enough, this movement can blur the image, potentially creating elongation in the direction of movement. However, some exposures were short, less than 1 minute, which was insufficient for significant blurring, and elongation was observed consistently among different observers with various equipment in different locations. One of the observers, going by the name Red Collie and introduced as Dr. Horace Drew, actively commented on the distribution of color. Drew published enhanced versions of several amateur images showing a white center and green periphery. He claimed that if the object is a small spherical core surrounded by a large green halo, then looking at it through a telescope that slightly blurs the image due to atmospheric turbulence and instrument limitations you should predominantly see a green blur. The white color should not dominate the center if the area of white glow is smaller than the area of green glow. Professional astronomers objected that comas are not uniformly bright. They are densest at the core and fade with distance. If you have a bright core surrounded by a less bright halo, even if the halo is green and vast, the central brightness from the core will dominate the images unless exposures are specifically calibrated to reveal the faint extended glow. Most amateur images are optimized to capture the bright core rather than the faint outer coma, so the presence of white centers is not surprising. The discussion between Drew and other observers highlights a fundamental issue. The interpretation of astronomical images requires an understanding of the shooting process, instrument reactions, exposure settings, and applied processing. Two people looking at the same raw data can produce different processed images that highlight various features, and without agreed-upon processing standards, debates about what the images actually show become subjective. Amateur images also suffered from the signal-to-noise ratio problem. The comet C2019Y4 Atlas was never bright, its maximum magnitude reaching around 8 or 9, too dim for the naked eye, but it was visible through binoculars or small telescopes in the dark sky. Most amateur tools had limited sensitivity, requiring long exposures, the combination of several frames, and careful processing to achieve a clear image, each carrying the risk of artifacts. Professional observatories are equipped with large mirrors, the best cameras, operate in darker conditions, and have a decade of experience in calibrating instruments. They know the specifics of their telescopes, how to correct optical aberrations, how to align images to eliminate uneven sensor sensitivity, how to subtract the background glow of the sky. Amateur observers often lack the necessary knowledge or equipment. Their images are valuable for detecting and general characterization of objects, but not for detailed analysis of subtle structural features. Nevertheless, in the absence of professional photographs from Martian orbital probes, amateur observations became the only source of information for the public, creating a vacuum in which speculation thrived unchecked. If NASA or ESA had released at least preliminary high-resolution images, even unprocessed and calibrated frames, it would have helped anchor the discussion in reality. People could discuss what professional images show, but at least the discussion would be based on quality data. Instead, the conversation focused on heavily processed amateur images of varying quality, supplemented by fakes created by artificial intelligence, which were spread through social media algorithms aimed at engagement rather than accuracy. Loud voices did not always belong to the most informed. The most sensational interpretations received the most shares, making it increasingly difficult to separate truth, whatever it was, from the noise. Amateur observers tried to bring reason to the discussion. They published educational materials on astrophotography, explaining common artifacts and demonstrating how processing choices affect the final images. They demonstrated how easily complete structures can be created by overdoing sharpness, how cosmic ray impacts on camera sensors can appear as stars or anomalies, how diffraction spikes from telescopes can be mistakenly perceived as real features, but nuances do not go viral. Careful explanations receive fewer views than bold statements, and when people want to believe that something unusual is happening, they selectively trust the expert opinions they believe in. Skeptical astronomers become part of a conspiracy, while enthusiastic interpreters carry the truth. Common mechanisms for quality control in science, such as peer review and reproducibility, do not function properly on social media, where anyone can post anything, and algorithms amplify whatever generates clicks. A website has emerged dedicated to collecting and analyzing all available images of Comet Tri-1 Atlas. The site, run by a person calling themselves an independent researcher, has gathered amateur observations, professional press releases, scientific articles, and blogs. However, he also gave equal importance to unverified speculations and thoroughly verified data. A graph showing nickel radiation levels from a very large telescope was accompanied by images of hypothetical spacecraft created by artificial intelligence. The blending of reliable and unreliable sources created an environment where separating truth from fiction required expertise that most visitors lacked. As October came to an end and the Comet Tri-1 Atlas approached the Sun, observations from Earth became impossible. The angular distance from the Sun decreased below the threshold at which even specialized equipment could safely observe. By mid-October, the comet was lost in the solar glare from our side. He remained invisible until early December, when he appeared from behind the sun, and by that time the perihelion had already passed and the most intense activity had ended. This meant that the amateur observation campaign concluded just as the events became most interesting. The last images taken before the solar conjunction showed Comet Tri and Atlas brightly illuminating the comet, which was expanding and emitting an intensifying green light. All of this met expectations as the comet approached perihelion and more gases were released under the influence of solar heat. However, none of the final amateur images resolved the debates about its structural composition. They showed an active comet, bright and blurry, moving across the sky as expected. But the lack of prolonged observations from Earth meant that everything that would happen at perihelion would only be recorded by space probes. The Solar and Heliospheric Observatory SOHO, located at the Lagrange point between Earth and the Sun, had instruments capable of observing the area near the Sun. The Parker Solar Probe, during its close passes around the Sun, could catch fleeting glimpses of a comet. The JUICE spacecraft, heading to Jupiter but with a viewpoint beyond Earth's orbit, planned observations in November. These observations were critically important. They would capture Comet Tri and Atlas in its most active state, when solar energy reached its peak, when gas emissions peaked, when any unusual behaviors became most apparent. If the object was going to behave unexpectedly, fragment, maneuver, or show any characteristics deviating from normal comet physics, it had to happen at perihelion. October 29th approached as the moment of truth. On that day, the Comet Tri and Atlas will pass at a distance of 1.36 astronomical units from the Sun, within Mars' orbit, closer to our star than ever in billions of years of wandering through interstellar space. Closer than at the moment of formation around the star system from which it came, assuming that the star of that system was similar to, or cooler than our Sun. What will happen when gigawatts of solar energy strike its surface? Will it maintain its integrity, or will thermal stresses shatter the core into fragments? Will gas emissions increase predictably, according to thermal models? Or will steep power dependencies in the production of nickel and cyanide be extrapolated to even more extreme levels? Will the object continue its hyperbolic trajectory unchanged? Or will some non-gravitational forces from asymmetric gas emissions noticeably alter its path? Beneath all these scientific questions lay a deeper issue that no one wanted to speak about too loudly. Yet it was present in every discussion. If Comet Tri and Atlas were artificial, if some anomalies indicated technology rather than geology, was the perihelion event planned? An activation point? The moment when solar energy charging systems, dormant for billions of years in the cold of interstellar space, might awaken? Could something that resembles a comet from a distance turn out to be something else, under intense solar exposure? This assumption caused discomfort among scientists, as it pertained to a field where data was scarce and imagination filled the gaps. However, October 30th was approaching, and when it arrived, someone would surely be watching. Chapter 9. October 30th. The Moment of Truth. Perihelion is not just a point in orbit, it is a trial. For comets, it means maximum tension, maximum energy, maximum activity. The physics here is simple. Solar radiation follows the inverse square law at a distance of 1 astronomical unit from the Sun, which corresponds to the distance to Earth. The solar constant is about 1,360 watts per square meter, and at a distance of 1.36 astronomical units, where Comet 3I Atlas will reach perihelion, this value drops to approximately 730 watts per square meter. This is still a significant magnitude, powerful enough to trigger intense chemical reactions. For an object that has spent billions of years in the cold of interstellar space, where the temperature barely exceeds absolute zero and sunlight is almost imperceptible, this was a real shock. Even during his journey through our solar system from the orbit beyond Jupiter inward, 3I and Atlas never experienced such intensity. If the laws governing the production of nickel and cyanide prove correct, and these connections continue to operate in the future, then the perigee must provoke an outgassing explosion that surpasses everything previously observed. The Solar and Heliospheric Observatory has continuously monitored the Sun since 1995, located at the Lagrange point L1, about 1,500,000 kilometers from Earth, facing the Sun. SOHO has a constant view of the solar disk and the surrounding space. Her LASCO chronographs block direct sunlight to observe the faint corona and detect objects passing near the star. SOHO has discovered thousands of comets, most of which are small comets approaching the solar surface. and often disintegrating. The spacecraft was not designed for studying interstellar objects, but its location and instruments allow it to observe the 3I and Atlas as it passes through the inner solar system. The Parker Solar Observatory provided another opportunity. This NASA mission, launched in 2018, aims to get closer to the Sun than any previous spacecraft, studying the solar corona and solar wind from within Mercury's orbit. Her perihelion passages bring her to within 6 million kilometers of the solar surface, requiring a special thermal shield capable of withstanding temperatures above 1,000 degrees Celsius. However, Parker will not be at perihelion at the same time as the 3I and Atlas. The spacecraft moves in its elliptical orbit, and the time frames do not match. But the WHISPER instrument of the Parker mission, with its wide-angle imaging for the solar probe, has a field of view that captures objects in the inner solar system. Mission planners calculated that from late September to early November, the spacecraft WHISPER should be able to observe the comet Tri-I Atlas from at least peripheral positions, depending on the exact coordinates and targeting schedules. The problem with the observations conducted using SOHO and Parker is that their equipment is designed for solar physics, not for detailed studies of comets. The coronagraphs of SOHO have relatively low spatial resolution. They can detect the presence of a comet, assess its brightness, and track its path, but they are unable to distinguish the structure at the level necessary to determine the compact nucleus and extended coma, let alone shape or detect surface features. Parker's WHISPER has the best resolution, but it was optimized for studying solar wind rather than solid objects. When Parker's trajectory meant that any observations of the comet Tri-I Atlas would be made at unfavorable angles, the comet appeared against the backdrop of solar observations rather than as the main target. The spacecraft that could provide the best observations at perihelion is JUICE, Jupiter Icy Moons Explorer. JUICE was launched in April 2023 and was heading towards Jupiter on a trajectory that allowed it to be in an excellent position to observe the comet Tri-I Atlas in November, about 2 weeks after perihelion. At this moment, the comet will still be actively displaying itself, being close enough to the Sun to continue gas emissions, but far enough that JUICE instruments are not blinded by sunlight. JUICE is equipped with several cameras and spectrometers designed for studying icy moons, though the same instruments are perfectly suited for observing comets. The Janus camera system can capture color images with enough resolution to see structural details. The main spectrometer can analyze the chemical composition of the coma in the visible and infrared ranges. The UV spectrograph can detect gases emitting in ultraviolet. ESA confirmed that JUICE will start observations of comet Tri-I Atlas from November 7th until the end of November. They emphasized that this would provide the best views of the comet in its most active state, when the tail is fully developed and brightness reaches its peak. However, the JUICE observations will take place after perihelion. Whatever happens at the closest approach, the maximum solar heating will occur when no spacecraft can get an optimal view. SOHO can capture moments, Parker can take distant images, but detailed, high-resolution observations that could definitively answer questions about the structure, size, and shape of the core, whether the ejections are symmetrical or asymmetrical, will not be available at the time of perihelion. The ground astronomers were completely blind. The comet Tri-I Atlas remained on the far side of the Sun from Earth's perspective, hidden behind 147 million kilometers of scorching plasma. No telescope on Earth or in its orbit could see it. The geometry simply did not allow it. This observational gap irritated scientists trying to understand behavior at perihelion, but also created a strange situation for those who suspected that the object Tri-I Atlas might be artificial. If something was about to happen, if a maneuver was planned, or systems were to be activated, then the moment of maximum solar impact, when the object is hidden from direct view of the Earth, would be the optimal time. Some noticed this back in July when the trajectory was first calculated. One of the researchers mentioned it in his work, pointing out that the 3I Atlas will be occulted by the Sun from the perspective of Earth during its perihelion. If you want to conduct operations without being seen by one of the planets, it is wise to arrange the perihelion so that the planet cannot see you. Of course, this assumes that the trajectory has been designed, which remains purely speculative. Natural orbits do not take into account the observational geometry from Earth. The fact that perihelion occurs when Earth cannot observe it is merely a coincidence, a consequence of when 3 Atlas moons entered the solar system and the trajectory they chose. Reading intentions in this requires faith that the entire journey was planned. which is an unfounded assumption. However, speculation existed. Online forums discussed this extensively. What if the 3AI Atlas used the maneuver of solar birth? The effect of solar birth is a real phenomenon in orbital mechanics. If you have a propulsion system and you launch it while deep in a gravitational well moving at high speed, you achieve a greater change in kinetic energy than if you launch the same propulsion system in open space. The most effective maneuvers are conducted at perihelion. If 3 Atlas ships wanted to change their trajectory from hyperbolic to a bound orbit that would keep them in the solar system, the best place for this maneuver would be at perihelion. You would achieve maximum efficiency from your propulsion, regardless of its shape, and if you synchronize it so that Earth cannot directly observe the maneuver, you will have plausible deniability. By the time you orbit the Sun and the Earth can see you again in December, the maneuver will be complete. You will be on a new trajectory, but observers will need time to calculate your new orbit and realize that it has changed. This is the realm of science fiction. There was no actual evidence of deliberate maneuvering, but the scenario was physically plausible, making it appealing to some. The natural expectation of perihelion was also dramatic. If the three-eyed Atlas was a comet, and if the steep degrees of dependency in the production of nickel and cyanide continued, then perihelion would have to cause a massive release. Production rates increased 25 times from the end of July to the end of August. Extrapolating this curve to perihelion, one could assume that production rates could increase tenfold or more. Such a level of emission could significantly alter the appearance of the comet. The comet's coma began to expand, possibly covering hundreds of thousands of kilometers. The tail, which had previously been barely noticeable and short, was now sharply extending as the solar wind and radiation pressure pushed dust and gas away from the core. The brightness of the comet was increasing, and it might have become visible to the naked eye if it weren't hidden behind the sun. Thermal stress could also lead to core fragmentation. Many comets break apart at perihelion when heating causes internal pressure to rise faster than it can be released through surface vents. If 31 atlases had structural weaknesses, if their core was a loose aggregate of smaller pieces weakly bound together, then the tension at perihelion could shatter them. The events of fragmentation look impressive. The nucleus splits into 2 or more parts, each developing its own coma. Brightness can sharply increase as fresh, icy surfaces become exposed to sunlight. However, fragmentation also signifies the beginning of the end for the comet. Particles disperse into subsequent orbits. Their total surface area increases, and they sublimate faster than if they remained a single body. Fragmentation is a sentence for comets, though less instantaneous than immediate destruction. Will 31 atlases survive at perihelion? The answer to this question could provide information about its structure. A cohesive, solid core, whether stone or ice, should survive, while a loose mass would not. If it were artificial, if it had an internal structure ensuring strength greater than that achievable by random aggregation, it would also reflect on its survival. The waiting was hard. October 29th came, the day passed. 31 atlases raced through perihelion while Earth remained unaware, turned in the wrong direction, with the sun obscuring the view. Spacecraft collected data from distant or oblique observation points. Somewhere in the inner solar system, hidden from our eyes, something was happening to an object that had traveled billions of years to reach this moment. The sun's warmth evaporated the ice, creating pressure inside the core as gas expanded, material being pushed into space by sublimation, thermal expansion, and relentless solar radiation pressure. Solar atoms, if the laws of force were maintained, were ejected at an unprecedented speed, glowing green under ultraviolet radiation. Synthesis radicals formed and dissociated in complex chemical cascades. Particles of dust rose from the surface, carried away by elusive gases, catching sunlight and reflecting it back into space. Then perihelion passed. 31 Atlas began their return journey. The distance from the sun started to increase. The influx of solar energy began to decrease. The bright activity of the perihelion gradually subsided as the comet moved back towards the cold outer solar system. But processing the observations took time. Data from SOHO had to be transmitted to Earth and analyzed. Observations from Parker were subject to analysis. The spacecraft could not transmit data in real time. Information had to be stored, compressed, and sent back to Earth through deep space network radio telescopes that received and decoded the data. Then scientists needed time to interpret what they saw. In early November, the first observations at perihelion were expected. The spacecraft JUICE received its data in the second week of November. Finally, in early December, 31 atlases would appear from behind the sun from Earth's perspective, allowing ground telescopes to resume observations. The appearance of the comet after perihelion, its brightness, spectral characteristics, and trajectory will all be carefully measured. If it looks like a normal comet after perihelion, active but following predictable patterns, it will provide one answer. If it breaks, it will indicate internal weakness, a natural structure unable to withstand thermal loads. If its appearance changes, if its chemical composition alters, if the trajectory shows unexpected deviations, it will raise new questions. The wait for December felt endless, weeks of uncertainty relying on incomplete data from devices not meant for this task, watching online speculation grow while concrete information remained scarce. Scientists tried to manage expectations, reminding the public that data processing takes time. Preliminary results can be misleading, and good science requires patience. It's hard to endure when the stakes are high, when an interstellar object could become the most important astronomical discovery of the century or turn out to be nothing special, when the answer could redefine humanity's place in the universe or simply add another dot to our catalog of comets. October the 29th came and went. The moment of perihelion became part of history, while 31 atlases, regardless of their true nature, continued their journey through space, carrying their secrets into the darkness beyond the sun, waiting for Earth's orbit to align again, eager to reveal whether it survived, whether its nature changed, whether the moment of maximum solar impact triggered something unexpected, waiting to partially answer the questions that had accumulated over months of observation and debate. What will happen if we make a mistake? This is a thought experiment that philosophers and scientists sometimes pose when discussing existential risks. Imagine you are given a sealed box and told there is a 10% chance it contains something that could destroy human civilization, but a 90% chance that it is harmless. Would you open it? Most people would say no. The asymmetry of outcomes makes caution reasonable. A 10% risk of catastrophe outweighs a 90% chance of nothing. Now let's change the experiment. The box will open automatically in a month. You cannot stop it. You can study it from the outside, conduct tests, gather information that may help you prepare for what is inside. Will you look? Will you measure? You are trying to understand, even if that understanding may cause anxiety. Humanity is in such a position regarding the object called the Tri-Eye Atlas. This object moves through our solar system on a trajectory that we cannot change. Ultimately, it will leave, continuing its journey through interstellar space. We can observe it or ignore it, gather data, or remain in ignorance, but we cannot make it disappear. The analogy with the Trojan horse, brought up by Avilueb, has historical significance. According to legend, around 1200 BC, the Greeks besieged Troy for 10 years unsuccessfully. Then they built a giant wooden horse, left it at the city gates as a supposed tribute, and sailed away. The Trojans, believing they had won, brought the horse inside. At night, Greek soldiers hidden inside opened the gates for the returning army. Troy fell because it accepted something incomprehensible. If 3 artificial atlas eyes exist, and if some of their observable properties indeed indicate technology rather than geology, their purpose remains unknown. By default, the optimistic scenario suggests scientific curiosity. An advanced civilization sends probes to explore and gather data from other star systems, similar to how we sent the Voyager and Pioneer probes from our solar system. A peaceful exploration, without hostile intentions. But this is merely speculation. We have no way to verify intentions. An object that looks like a comet, but is actually a probe, can gather reconnaissance data about our solar system, Earth, and whether life exists here. He can send reports, transmitting data through methods we cannot detect, or on timescales too slow for us to notice his brief presence. Or it could be something more directly threatening. An article co-authored by Loeb with Adam Hibbard and Adam Kroll titled, "Is the Interstellar Object 3 AI Atlas Alien Technology?" explores scenarios where trajectory and time were not random, where the close passages to Mars, Venus, and Jupiter serve purposes beyond chance, where the perihelion behind the sun allowed maneuvers or actions that Earth could not observe. The article cautiously identified itself as a pedagogical exercise, exploring possibilities rather than asserting probabilities. However, it described scenarios that induced anxiety. If any civilization wanted to scout our solar system, the trajectory of 3 Atlas would be almost optimal. Retrograde orbits are harder to intercept. These passages near several planets allow for gravitational assist to alter trajectories or deploy smaller probes that could enter the planet's atmosphere. The article calculated that if a three-body atlas uses the maneuver of reverse solar slingshot at perihelion, it could potentially change its trajectory from escape to a bound orbit, remaining in the solar system indefinitely. The optimal time for such a maneuver would be when the Earth could not detect it, coinciding with periapsis. Did this happen? Currently, there is no convincing evidence. Accurate measurements of position over time are necessary for trajectory calculations. Until 3 alien atlases emerge from the solar conjunction in December and become observable, astronomers will not be able to definitively determine if their trajectory has changed. Even if a change has occurred, it can be explained by the gravitational forces from the asymmetric jet. The object regularly experiences slight trajectory changes due to the thrust from the ejected streams. To distinguish natural trajectory changes from artificial ones, detailed observations are needed regarding where the emission occurs, how symmetrical it is, and whether the force pulls in the direction of the visible streams. Such an analysis requires time and quality data, but the scenario raises uncomfortable questions. If an interstellar probe wanted to remain in our solar system, perhaps to continue observations for decades or centuries, how could we stop it? The answer is simple. We couldn't. Our faster spacecraft move at speeds of several dozen kilometers per second. 3 alien ships travel at over 60 kilometers per second relative to the Sun. We have no way to intercept something moving at such speeds. There is no propulsion system capable of matching this speed. There is no weapon that could reach it. Even if we found clear evidence of artificial origin, even if we were sure that the 3 alien atlases were technology from another civilization, our response options would be limited to observation and concern. We could direct more telescopes at it. We could try to establish radio communication, although the time for feedback with an object several astronomical units away would make conversation impossible. We could notify international organizations, convene emergency meetings at the United Nations, coordinate scientific responses. But in terms of real defensive measures, we have no options. If the intentions of the test tube were hostile, if it were created to assess our capabilities before some future action, we would be powerless to prevent what follows. This is why some oppose aggressive surveillance. If we are being studied, if our radio signals and television broadcasts have already announced our existence, does it change anything to direct telescopes at an interstellar visitor? Or does it simply confirm that we have noticed it and are paying attention, potentially provoking unpredictable reactions? Others hold the opposite opinion. Ignorance is not safety. If something potentially technological passes through our solar system, it is crucial to gather as much information as possible to understand its capabilities, composition, and behavior. This knowledge could prove crucial if similar objects appear in the future. We cannot defend against what we do not understand, but we can prepare if we learn enough. The philosophical implications go beyond immediate safety. Confirmation that the Atlas of Three Eyes is artificial would mean that we are not alone, not in an abstract sense of life existing elsewhere in the universe, but in a concrete sense of knowing another technological civilization capable of sending objects through interstellar space. This knowledge would radically change humanity's perception. We would no longer be unique. Our achievements in science, technology, art, and philosophy would need to be understood against the backdrop of others, as they likely achieved more, having mastered interstellar travel while we barely reached our own satellite. Some might perceive this as a positive humility, a reminder of our humble place in the vast universe, a stimulus for our growth as a species to overcome our divisions and conflicts. Others, however, might see it as a threat. If we are not alone, and if we are being watched or evaluated, our future may not be entirely in our hands. The social consequences of this revelation will affect all institutions. Religions will have to reconcile their theologies with the existence of extraterrestrial intelligence. Governments will be questioned about why they were unprepared, why they did not take the possibility seriously. Scientists will shift priorities, focusing on understanding the consequences, on whether communication is possible or if silence should be maintained. The economic consequences may be subtle but significant. If there is a technology that significantly surpasses ours, it changes the approach to long-term investments. Should we continue to develop certain technologies knowing they might become obsolete, if we ever gain access to alien knowledge? Or should we accelerate research, trying to advance as quickly as possible to close the gap? Military strategies will require a complete rethinking. If there are potential adversaries with capabilities we can barely imagine, then Earth's geopolitical conflicts become almost insignificant. There is no need to worry about territorial disputes with neighbors when there may be interstellar forces watching over your planet. But all of this presumably relies on the fact that the Atlas of Three Eyes is artificial, and the likelihood of this, according to most scientists, remains low. Anomalies are real. Observations cause confusion, but natural explanations, though strained, are still more likely than artificial ones, as we have no prior evidence of interstellar probes. However, the cost of error in this case is asymmetrical. If we assume this is a natural phenomenon and are mistaken, we will miss the opportunity to learn, communicate, and prepare. We may remain unaware of its presence in our solar system until it manifests in a way we cannot ignore. If we consider this potentially artificial and are mistaken, we will waste additional observational resources, publish incorrect articles, and appear foolish in the eyes of future historians. The price of what we will consider natural when it is artificial is potentially much higher than the price of what we will consider artificial when it is natural. This asymmetry requires increased caution, attentiveness, and analysis. She justifies a serious attitude towards possible scenarios, even if the likelihood of their realization seems low. In early December, when the three eyes of the Atlas become visible from Earth again, when telescopes can resume observations and calculate its post-perihelion trajectory, we will have new data. If the object disintegrates, it will strongly indicate its natural origin. Artificial probes usually do not break apart from thermal stress. If its trajectory does not show unexpected changes, it will increase the likelihood that this is a comet moving solely under the influence of gravity and gas release. If its chemistry remains strange, if nickel emissions continue, if color and structure raise more questions than answers, then the debates will continue. And if this is the scenario that troubles some scientists, if the trajectory shows changes incompatible with natural gas emissions, if the object maneuvers in a way that requires acknowledgement of a deliberate push, then everything will change. The Galileo project established to study potential evidence of extraterrestrial technology through the investigation of interstellar objects and monitoring unidentified aerial phenomena includes 3 observatories equipped with instruments designed to detect and characterize anomalous objects. If the three eyes of the Atlas reveal something unexpected upon exiting the solar connection, the telescopes of the Galileo project will be on alert, along with dozens of professional observatories worldwide and thousands of amateur astronomers with their equipment and desire to understand the cosmos. The observational campaign for the reappearance of the Atlas three-eyed object will be one of the most coordinated in the history of astronomy, driven not only by scientific curiosity, but also by the persistent possibility that this object may be more than it seems. Between now and December, the waiting continues. Data from the perigee arrives slowly. Observations from the satellite are analyzed frame by frame, searching for something unusual in the appearance or behavior of the comet during its close approach. The spacecraft Jupiter prepares its instruments for November observations. Mission planners calculate optimal pointing angles for maximum data quality, and people wonder. In online forums and cafes, in university classrooms and government briefings, the question remains, what are the three eyes of the Atlas? A stone or a probe? An ancient comet or ancient technology, a natural wanderer, or an artificially created explorer? The answer, when it appears, may not be final. Science rarely provides absolute certainty, especially regarding objects we can only observe from afar with limited data. However, the search for answers, the process of gathering clues and assessing possibilities continues, because understanding what passes through our solar system, whether we are alone or being observed, and understanding the nature of interstellar visitors touches on the deepest aspects of human curiosity and our place in the cosmos. December approaches, the comet moves through space, and we wait for it to appear from behind the sun. Here we are in this unusual moment of human history, watching the sky with tools our ancestors could not even dream of, seeking answers to questions beyond science that touch on something deeper. 3 Atlas eyes continue their journey. Indifferent to our debates, fears, and hopes, it moves through the darkness toward the sun, carrying with it the truth it holds, waiting for the geometry of orbits to bring us to a new coincidence. We have followed the clues together. Extended photographs from Mars that sparked an unresolved debate. Coordinated silence from space agencies worldwide, rivals united by their reluctance to share. A green glow appeared without the molecules that should have caused it. Nickel, breaking into space challenges simple explanations. 7 statistical improbabilities accumulate like evidence in a trial where the verdict remains uncertain. Political whispers at levels where decisions about information disclosure are made. Amateur astronomers fill the void with images of varying quality and interpretation. And the perihelion passage, hidden from our eyes, where solar energy has crashed onto a surface that has known only the cold of interstellar space for billions of years. There are 2 options left: an elongated object or an optical trick, an ancient comet with chemistry we have never encountered, or something that merely resembles a comet but is something entirely different, natural or created, random or intentional. Perhaps December will bring clarity. Perhaps the observations after perihelion will reveal fragmentation, chemical changes, trajectory deviations that will finally tip the scales in favor of one interpretation, or the uncertainty will persist, and we will add 3 Atlas eyes to the growing collection of cosmic mysteries, where clues point in different directions, and certainty remains elusive. What we know for sure is that something from beyond our solar system passed through it, something ancient, beyond our understanding, carrying materials formed around another star, shaped by processes billions of years removed from our experience. Whether it is a messenger or coincidence, carrying information or merely reflecting sunlight, it reminds us that the universe is larger and stranger than our daily lives allow us to remember. Thank you for spending these hours with me, exploring the clues and consequences of this remarkable visitor. If you found this journey interesting, I would appreciate it if you rated this video and subscribe to the channel. This will help more people learn about these stories and support the creation of deeper investigations into the mysteries that surround us. The content presented here is based on publicly available data, published research, and documented observations as of October 2025. Public understanding evolves as new evidence emerges, and interpretations that seem reasonable today may be revised or disproven by future discoveries. This video explores possibilities and offers various perspectives, but does not make definitive statements on issues that are still under investigation. Always consult multiple sources, maintain skepticism, and remember that the most honest answer to many questions about the 3-eyed Atlas is still, we don't know. The night sky continues its ancient rotational path above us. The stars trace their paths. Planets wander against the backdrop of constellations. And somewhere beyond the blinding light of the sun, an interstellar guest continues its journey through our cosmic neighborhood, keeping its secrets, waiting to reveal whether the strange photographs from Mars showed something profound or merely taught us about the limits of perception. Good night, and don't forget to look at the skies.